Hello everyone. So in the previous session, we have started our discussion on logistic regression. So in the logistic regression, I said do not get confused by this term regression. This actually is a classification algorithm. Okay, and classification algorithm, it assumes that data is linearly separable. So you all know the meaning of linearly separable. So now I'll just revise a bit and we'll see what are the things that we covered so far. So we said we have to maximize this. So yi w transpose xi. So when a classifier is there, we have a hyperplane. We call this pi, and this is represented by this pi, and it has two parameters, w and this b, weight and bias. So in the 2D case, this y is equal to mx plus c is what represents the line. So here with this y is this m is slope and c is the intercept. If you give me this m and c, I can uniquely give you a line. Okay, and similarly, if you are in 3D, 4D, and D, we call them hyperplane. So there we have this vector w and we have this bias b. Okay, so in that, how do I represent the hyperplane? That is w naught plus w1 x1 plus w2 x2 and so on. If it's an nd hyperplane, w1 xn is equal to 0. This is the equation of hyperplane. So this we have written a succinct way like this: w naught plus w transpose x. So this is capital X. So basically x has components x1, x2, x3. This is equal to 0. So w is equal to w1, w2 and so on till wn. Okay, and x here is equal to x1 till xn. That's why we transpose the w. So we'll transpose it. It will become like this. So this is our w transpose. So this is our x transpose. So x basically is a column vector. This is a vector. So now when we have this w, so this will become w is like this and x is like this. Okay, so this is our w1 till wn. This is our x1 till xn, and this is our w naught. This is equal to 0, and that's why I have written. So if you just expand this equation, it will become this. Okay, this is w naught. So in nutshell, we'll write it w transpose x plus instead of this w naught, we sometimes write it as b bias. This is equal to 0. So if I know this w transpose, if I know this w vector, and if I know this b, that means I know the hyperplane uniquely. Okay, so if data is like this, so if we have positive class data, if we have negative class data, okay, we draw a hyperplane. So this is w, this is called as positive half space. Okay, and this part over here is called as negative half space. So in logistic regression, the thing that we discussed was, so w transpose xi, if we have a data point xi, okay, so over here, if this is our data point, so we said, let's suppose this is a data point. So if we perform the dot product, that's basically we are computing distance. If this is positive, this will be like for positive class, and this is negative for the negative class. Okay, this is negative for the w transpose xi is less than 0. This is for negative class, this is for positive class. So we know the labels yi belongs to +1 or -1. Yi belong to +1 or -1. So if I write like this, yi w transpose xi, if it is greater than 0, this means correct classification. This is correct classification. Otherwise, it's a misclassification. Okay, and then we said that we have to maximize this. So we have to get maximize this yi w transpose xi. I is equal to 1 to n. For all the points, we have to get maximum value of this, because as you know that in order to classify a point correctly, okay, this should be greater than 0. This should be a positive number. Greater than 0 means it should be a positive number. So that means that if for all the points we should get, for most of the points we should get these positive values. That is, we should maximize this equation. So how to maximize this? Then I said that as this yi and this data is fixed, label is fixed, data is fixed. So what you can write is, we say argmax of w summation of I is equal to 1 to n yi w transpose xi. So you should maximize this equation for such a w. That means you should find such a w which maximizes this equation. Okay, and we call it w star, the optimal w. That means that have a hyperplane which should give us the for which classification accuracy should be high. That is, it should classify most of the points accurately. And how to do that? You have to maximize this equation. Then we saw a problem with this equation. We saw that this is affected by outliers. This is sensitive to outliers. Okay, then we said in order to build a function, we should somehow pass this input through a function. Okay, what we call a squashing effect. We should have a function like this. We should have a tapering off behavior. So it should initially grow linearly, then taper off. Similarly for this, and then we find a function which is called as logistic function, a sigmoid function, which is f of x, that's equal to 1 divided by 1 plus e to the power minus x. This was a sigmoid function. Okay, and we said now we'll not optimize this. So what we'll do is we'll optimize argmax of w. We'll find such a w for which this sigma of this yi w transpose xi, sigma of yi w transpose xi, this basically gets maximized. So if I just expand it, so this means find such a w. Argmax basically means find such a w for which so this is summation of this, summation of I goes from 1 to n for all the data points. Argmax of for all the data points I goes from 1 to n, this means for all data points, and then apply this sigmoid function. So how to apply sigmoid? This means 1 divided by 1 plus e to the power minus yi w transpose xi. Okay, this is what this is what we'll optimize now. So this function, is everybody clear with this so far? This is just the revision of the previous lecture. I think everybody is sort of clear on this if you have watched the lecture. So I'll write this equation again. So what we have to optimize basically was this. So in order to find this w star, so we're saying that we have to argmax of w, find such a w such that for all the points, always say that read these equations as if you are reading the English, then only you will understand this. So this is just a succinct representation of that English. So w star, that means optimal w is equal to find such a w. Argmax means find such a w which maximizes this. What should we maximize? We should maximize this 1 divided by 1 plus e raised power. I'll write e raised power exp. This means e raised power of minus yi w transpose xi. So this is what we discussed so far in the previous session. So this is what we have to optimize. Okay, now we'll do one more transformation of this, because you now know that we have to find this argmax. So what we'll discuss is that we somehow will apply log onto this. Okay, we'll apply log onto this. We'll get into a neat and clean form. And why can I apply log? First, let me discuss why can I apply log. Why can I apply log on this function? Okay, let's suppose if you have a function x square. If you have function x square, so you know that function x square, this function looks like this. This function x square looks like this. Okay, it's a parabola, it looks like this. So this point over here, okay, this is its minimum point. Or if you just write minus x square, it will be like this, and this will be its maximum point. Okay, so this is our x square and this is our minus x square. So if I show you on that Desmos calculator, so I just want you guys to have these function shapes in your mind so that it becomes easy to understand these things. Give me a second, I'll show you that. So if I draw a function, let's suppose y is equal to x square. So I draw this function y is equal to x square. So can you see it over here? So this is this here over here is the graph of function x square. So if you take this graph x square, so you can see the point over here is a minimum point. So here is the minimum point. Point over here is the minimum point. So why does this minimum exist? At x is equal to 0. So for function, if f of x is equal to x square, so the minimum value is at x is equal to 0. Okay, so where is the maximum value? It has no maximum value because both of these goes to infinity. Okay, now if I somehow change this, so if I write y is equal to minus x square, so this is minus x square, you will see the function will flip. Okay, now you are seeing that function flipped. Now for this minus x square, the maximum point is over here. Maximum point, x is equal to 0, it has maxima. Okay, so this is f of x is equal to minus x square, this f of x is equal to x square. Okay, I hope that these things are clear. I'll show you these graphs. So why am I discussing these things? Because let's suppose now if I apply some function onto this, so if I apply log of x square, so we have x square function. Okay, so if we have function x square, so this is our function. So you know that now that the minimum of this function lies at x is equal to 0. So if I apply log onto this function, so log of this function, log again is a function. So I have a function f of x. So if I apply g of x function on this, okay, there is a function g function. Okay, I am applying this function on this. So what I am saying is, if I have to compute arg max or arg min of this function x square, okay, I have to find arg minimum of this function, arg min of x. So what will be the value? The value will be 0, because at 0 we are getting the minimum value for this function x square. So what I am saying, there are a class of functions which we will call as monotonic functions. Monotonic functions. So what are these functions? So we have two types of monotonic functions. Now they are monotonic increasing function or monotonic decreasing function. So let's suppose I have two values, x1 and x2. If this x1 is greater than x2, okay, So that means if I take a monotonic function, let's suppose that function is g, so then g of x1 is also greater than g of x2, okay, or even equal to. So what in graphically, if I show you that, so graphically if a function is like this, which is always increasing, we call it monotonically increasing or non-decreasing function. So that is like this. So let's suppose if you see a function like this, okay, which is not going down, it basically sometimes it becomes constant but still goes up, so it is always increasing, it is non-decreasing function. So a log is such a we have a log is a monotonic function, okay. You don't see that non-convexity in this in the log function. So so if I by that I mean that if I have to find this argmin of x square for x, so we get x at x is equal to 0, we get the minimum value of that function. So what I'm saying, if you apply a monotonic function onto this function, so we have this function, so now if you apply log of this x square, okay, and you still got argmin of x, the value will be different, but the point which minimizes this value will be same. So if you tell me what is the maximum, what is the minimum value of x square, like what's the minimum, or what's the minimum value, the minimum value can be different. So minimum value of this and minimum value can be different, but the point which minimizes the value will be same for both of these. That's the meaning of these monotonic functions. If I apply log to this, log has this beautiful property. So when you apply the log, the value may change, the maximum value or minimum value may change, but the point at which it is maximized or minimized will remain the same. How many of you understood this point?
Yes, sir.
So let me show it graphically to you. So let's suppose again we had this. Let's bring it right here. So I'll zoom it a bit. Okay, so let's suppose this was our graph, because I wanted to also show you this. So this was our function y is equal to x square. So now you know that this at this point, if you see at this point, so the function has value at x is equal to 0, this gets minimum value. Now I apply log on this function, so log of x square. So you still see that at x is equal to 0, the function is minimum. So value got changed, the minimum value shifted towards here, but still if you see at x is equal to 0, the function is getting the minimum value. Okay, that's what I mean by that. The minimum value might be different, but the value at which the value got minimum, that's arg min or arg max will remain the same. Similarly, let's suppose we have a function, we have this function minus x square. So you know that the maxima of this function is at x is equal to 0. Okay, if you see to over here, the maxima is at this point. Okay, now if I apply log onto this function, if I apply log of this, so log of minus x square. Okay, this basically is, I think, 1 by that, and you will still see that the whole of this graph will become like that, 1 divided by, let's suppose, x to the power 2. I'll just remove this. Okay, you can see this, because a minus log of x square basically is this. So this is the function. So you can clearly see over here is that still the maximum value, maybe maximum value got changed, it got to some infinity or something, whatever, but the value at which we attain the maximum point is still 0. So that's what I wanted you to understand. That is the concept of monotonicity. So if you have monotonic function, if you apply onto this, maybe maximum minimum may get changed, but argmin and argmax do not get changed. Argmin and argmax basically gives the value at which the function has minimum or function has maximum. I hope you understood this. Again, to just wrap this thing up, so what I'm saying is, so if we have a function f of x, so if I'm trying to find argmax or argmin of this function for some value x, so I'll get a value of x for that point. It is not a maximum value, so there's a difference between max of f of x. So the meaning of this is, what is the maximum value that f of x can attain. Okay, if we have a function, let's suppose some function we have, and what is the maximum value that this function can attain, so that is max of f of x. But if I ask you a question, at what point, at what x is the maximum value attained, then we say that's argmax. Okay, so in terms of naive base, I said probability of yi given x. So what is the maximum value of this? The maximum value can be 1. Okay, if I write maximum of this, so maximum value of this probability can be 1. But if I write argmax, so argmax of probability of yi given x. So basically what I am saying is, I am saying what yi or which I makes this value maximum. That's the difference between argmax and argmin. I hope that you understood this. Okay, now if we have a function f of x, and we are saying that find argmax of x, find argmax of this f of x, or find argmin of this f of x. So that means you will find such an x, let's call it x dash. This x dash is such a value, when you input this to a function, this gives the minimum value. This actually is not the minimum value, but this is the function input. It is that input on which this function gives the maximum value. Similarly, if you have argmax or min of x or min of the f of x at x, so we'll call x double dash. So this x double dash is that value which you give to the f of x, it will give you the minimum value. Okay, that's the difference between. Now what I said is, I said log is a monotonic function. So if you have a function like g is a monotonic function. So if you say g of f of x, okay, and you still want to find this argmax for x, you'll still get x dash value. I just showed you for the x dash. You can prove it mathematically, but I just am giving you the intuition, and you can just take time and prove it mathematically then. Now g is a monotonic function, but there is a condition that it should be monotonic function. Monotonic function. Okay, and similarly, if we have argmin on this f of x, so if we apply this g of x, g of this function, so again this will be x double dash. Basically, the point at which we are getting the maximum and minimum value would not change if you apply a monotonic function. That's what I'll do over here, because I want my equation is like this. So my equation is like this. So my equation is w star optimal w is equal to, you take arg max of w, you take such a w for which summation of for all the points I is from 1 to n. This means for all the points, so I should get this value as maximum 1 divided by 1 plus exponent of minus yi w transpose xi. Okay, this I have to maximize. But this equation looks a little bit tedious. So I know that if I apply log on this function now, if I apply log, what will happen? This w star will not get changed, because I am interested in this w. I am not interested in the maximum value. I am interested in what w maximizes this. So I can apply log onto this, because this won't change. Okay, so when I apply log, is everybody clear on this point? If I apply log, there will be no change in this. There will be no change in basically in our what I can say in our end goal, because we are finding a function which is a monotonic, and log is a monotonic function. Is it clear?
Yes, sir.
Okay, now I can apply log onto this, and I can show you how this optimization problem will get changed, and because it will become easy that way. So if I apply that, and then it will become easy. Let me show you that. So I'll apply log on this, because now the condition is that when I apply log, this w star will not get changed, because w star gives you the that point on which this value gets maximized. Okay, now I'll apply log. Okay, so applying log on this, the w star is equal to argmax w of log of this whole equation, this equation. Okay, let me write it again. Summation of I is equal to 1 to n, 1 divided by 1 plus exp of minus yi w transpose xi. So I apply log on this. Okay, so what will happen is, so now you know that what is log of 1 by x? That's minus x. If you know that, if you have log of 1 by x, that is minus log of x. You know this property, because log of this can be written as log of x raised to the power minus 1. Okay, and then you know the property of log a to the power b is equal to b log a. Okay, just a side note. I hope that you guys know this. So log of 1 by x can be written as this. So that's what I'm writing over here. So argmax of this log, the summation can be taken out though. Okay, so I can just apply this. I can take the summation out. I can write log it over here. So I'll write log, and I'll take the summation out, because I just wanted to do on this argmax of this. So I'm applying log. Now what will happen is, this will become negative. So w star is equal to, this is my equation, argmax of w over all the points, and I'm applying log onto the function 1 divided by 1 plus exponent of minus yi w transpose xi. Now you know that when you apply log onto this, what will happen is this will become minus of this. So this will become argmax of w summation of I is equal to 1 to n, and this will be minus. So I'll take minus over here. Let's suppose minus of log of 1 plus exp of minus yi w transpose xi. How many of you are clear with this? How many of you are clear with this? I just took log outside this, so I just expanded this. I used the expression. Are you clear with this?
Yes, sir.
Yes, sir.
Okay. Now I showed you one more thing. Like unintentionally, I showed you that. I said if we have a function x square, okay. So for x square, we had minima exists at x is equal to 0. So if I had minus x square, okay. Now maxima is at x square. So if you change the sign of function, so what I'm saying you, if I have my f of x, okay, for that let's suppose minima exists as x dash. Okay, for if I have to find the minima, and minima exists like basically argmin value gives me x dash. If I have f dash of x, now this will become maxima. This point will become maxima of that. So that I showed you with x square and x. You can also prove it easily. Mathematically, you can easily prove it. If I have a function, if there is a point at which minima exists, and you can just flip the function, write the negative sign, and you can show that now that point is the maxima. Okay, if it was initially minima, and if you just flip the sign, it'll get converted into maxima. That is what I showed you in terms of this x and x square. So I showed you that x square has a function like this. So this is our x square. So here we had a point. Let's call this x dash. Okay, and this point was the point at which we had the minimum value of x square. So now if I change this function, if I change minus of fx, that means minus x square. So that means we have a function like this. So same point will become the maxima. The same x dash will become the maxima for this minus x square. Is it clear?
Yes, sir.
Because in computer science mostly we do not maximize functions. What we do is we do minimization. Okay, that's why I'll take this negative sign out. I'll say I want to arg min of this. I'll say arg min. I'll take this negative. I'll absorb the negative sign. So what I will find is I'll say w star is now equal to arg min of w, and then log of 1 plus exponent of minus yi w transpose xi. Okay, everybody clear with this? Is everybody clear with this?
Yes, sir.
So this is our optimization problem that we have to solve. Okay, so this is the problem. Okay, so this is called as, sometimes we call this as logistic loss function. Okay, this is the loss term. So this is loss. Okay, sometimes this is called as logistic loss. If you read some different textbooks, there they'll call it this is logistic loss, and here we have used this logistic function. Okay, so now you saw that we have to optimize this. Okay, somehow we have to find a minimum value, such a minimum value of w such that the value of this gets minimized. So we had a maximization problem, we convert into minimization problem because we had a minus in that, and you will see nearly 98% of times in computer science you will do minimization. Okay, how to do minimization? We'll just use the differentiation that we have seen, differentiation, and sometimes you use double derivatives to confirm this thing. Okay, I hope that this is clear. So this equation over here, if you see it over here, this is our loss function of this. So what is so special about this? If you see this one was not here. So initially, originally, what was our function? We had argmax of, we had something like this, argmax of, we want to maximize this yi w transpose xi. This is what we wanted to maximize. Okay, this is equivalent to arg minimize w but minus of this. Okay, isn't are they both equivalent? So if you see this equation, so this was the original equation. I want to maximize this for all the points. This is also for all the points. So how many of you agree with me that both of these are equivalent? Both of these will give same w star.
Yes, sir.
Okay. So now if you see this, if this one was not here, let's suppose if this one was not here, this log and exponent will cancel. So what will happen is, so if this one is not here, this w star will become again, this log and exponent will cancel each other. Okay, this again is a summation. Sorry, I'm just writing it now. So this is summation actually. Okay, this log and this exponent cancel out, and what they'll do is they'll again form the same equation. They'll again form summation of I equal to 1 to n yi w transpose xi, and we have to find arg min of this. Arg min of this. This is basically minus, negative of this. Let's call this negative. Okay, arg min of w. So did you see that we basically arrived at the same equation again if this one was not there? What is happening with this one? It is just becoming like it is not now sensitive to outliers. It is becoming like resistant to outliers. Like to some extent, it still has the problem with the outliers, but it is way much better than this function. Okay, this function is sensitive to outliers. Sensitive to outliers. Okay, but if you see this function, this will be like less sensitive to outliers. If you have an outlier, still it will take care of that. So the function that we just changed, this one got introduced in this one when once we applied this log and everything. Everybody with me so far?
Yes, sir.
Yes, sir.
So this is the function that we have to. So this can be asked even a question. So what is the function that you have to minimize, or what is the function for this logistic regression? So again, I'll write it. This is w star is equal to arg minimum of, you have to arg min, that is you have to find such a w which minimizes whatever comes after this. You have to minimize log of this. You have to minimize, take summation over all of this, take summation over all the points from I is equal to 1 to n. These are all the points, and then take log 1 plus exponent of minus yi w transpose xi. Okay, so this is our logistic. This is our the optimization function for logistic. Now we'll see the problems with that, and we'll have to see overfitting, underfitting. But before that, I want to have a discussion on this W. If this is clear, then only I can move ahead. So here is our problem. Now we have to find such a W which minimizes all of this. Okay, which minimizes this. Okay, now let's focus our attention onto this. If you see this part of the equation. Okay, and we'll see how to minimize, what should be the value of W, and then I'll show you the problem that will happen there. So let's suppose we have this log of 1 plus exp of minus yi w transpose xi. Okay, so you know that log is defined for positive numbers. Okay, so this over here, if you see exponent, it always is a positive number. Okay, this is a positive number always. So if log of 1, this is equal to 0. Okay, just focus over here. So log of 1 is equal to 0. So if you add a little bit to 1, this will be log of 1 plus. So 1 plus means any number which is greater than 0. So obviously it will be greater than 0, because log, you have seen the function, it basically is a monotonic function. If you give x value, if we have x1 that is greater than x2, then log of x1 will obviously equal to greater than log of x2. Again, to show you this function, because you must commit these functions to memory. Yeah, I'll show you that function again. So if I just draw the function log of x, see this function. So this function over here, if you see this, log of negative numbers is not defined. Okay, log of 1 is 0. So log of 1 is 0 over here. So after 1 you see this positive numbers. Okay, then that's what I was showing here. So this is the log function. Okay, it's a monotonic function, and when you give log of negative numbers is not defined, so log of 1 is 0. So whenever there is a number which is greater than 0, log will be always positive. So do you agree with me on this? Do you agree on this now? So log of 1 is equal to 0. So this is a positive quantity. Again, I'll show you the graph of this e to the power minus x. We'll see the graph. So now let us draw the graph of e to the power x. E to the power minus x. This is the graph. Okay. So if you see over here, this is always positive. If you see the y-axis of this, so these are the values of e. So these are the values of e. So they are values taken by this x. So this is e to the power minus x graph. So this is the x value. So whole of this is x, and you see this e to the power minus x always is on the positive side. Okay, so e to the power minus x is always positive. This is always greater than or equal to 0. Okay, you can see that over here, and sometimes it becomes 0. You can write greater than or equal to 0, and for when e tends to x tends to infinity nearly, so it becomes 0. Okay, so I hope that you sort of agree with me on this. So that's what I wrote over here. So if I again show you what I wrote previously, that was this. So this quantity over here. So this can be a number. Okay, and then this negative e to the power minus of this number will always be positive. So that's what I said. So e to the power minus of x is always greater or equal to, this is a positive number. So at worst it can be 0, that you say when x tends to infinity it can be 0. So now this log of 1 is equal to 0. Okay, log of 1 plus, so if you have a number which is little bit greater than this, or even a number which 1 plus means any number which is greater than 1, so this is greater than 0. Okay, so this quantity over here, so what is the least value it can take? So if this over here becomes 0, so if this exp of minus x becomes 0, then only it will take the value of 0. So the least value that this function can take is 0. So how many of you agree with this? Because log of 1 is 0, log of 1 plus is greater than 0. Now you know that for x, when it tends to infinity, then only will this value become equal to 0. But what is the value? The thing that we want, is we want to minimize this equation. Okay, what is the minimum value that this takes for a single point? Let's suppose for a single point, what is the minimum value that it takes? Do you agree that this is the minimum value it takes is 0?
Yes, sir.
Why? Because we have to somehow get this as 0, because log of 1 is 0 and we have to get this as 0. So when will this become 0? Again, just I am erasing these points because I think you understood it. So this is our equation. So here if you see this part, so this part is always greater or equal to 0, because you saw the graph. So this part over here, so this over here is always greater or equal to 0. Now you saw that log of 1 is equal to 0, and if you add a small quantity to this 1, this will become 1 plus, this will become a number greater than 1, so that will always be greater than 0. But our question says is that you have to minimize this function. So what's the minimum value that we can get? The minimum value that we can get is 0. Okay, because we have to somehow make this 0. Okay, let's see how to get that minimum value. So we have to make this exp minus x. So exp minus of yi w transpose xi, this should be equal to 0. When will this be equal to 0? When this whole quantity tends to infinity. So when will this tend to infinity? When, because this is constant, you cannot change this, because now this w has components, this has components like w1 w2. When this, all the components are either plus infinity or minus infinity according to the signs of these two. Do you agree with this? Wi should be either plus infinity or minus infinity. How many of you understood this part? Because I want to get this equation as 0. That's what my argument says. So argument says that you have to minimize the equation. Now I found that the minimum value of this equation is at 0. Is the minimum value is 0? Is at not at 0? It is 0. So how to get that 0? That 0 should be we'll get that if we make this 0. If we make this exponent of minus yi w transpose xi as 0. So how to make this as 0? When you make this whole term as infinity, you should make this term infinity, but you have no control over y and xi. That means you have to make this w vector as infinity. So how to make w vector as infinity? So it will be either plus infinity or minus infinity, because based on the signs of these numbers, so you'll accordingly adjust plus infinity minus infinity. How many of you understood this point? Tell me. This is really important. Somebody speak.
Yes, sir.
So one thing I'll tell everybody is, like, if I think Amira, Rian, you guys can speak. If you see thumbs up from everybody, you can say yes, everybody understood. Okay, then I don't have to switch the screen, because I am seeing at the OBS screen. I am not seeing at this Google Meet screen. I hope that this is understood by everybody, that if I have to sort of make this value as 0, if I have to make this value as 0, the whole of this term should be infinity. The only thing that will make this infinity is this components of this w's, w1, w2, w3, they should be either plus infinity or minus infinity. Why plus infinity minus infinity? Because based on this x, y, and yi. So there is a problem now. Now you see that you have to make all the values plus infinity and minus infinity. And now what will happen here is it will overfit. Okay, because you are getting all the training points correct. If you are making it such that because this w is basically a perpendicular vector to our plane, to our hyperplane. Now you will overfit the model. You are trying to capture everything. You are trying to classify every label correctly. Okay, you are trying so hard that you are making this as plus infinity. You are trying to minimize this function. Basically, you are trying to find such a hyperplane for which the distance to the points is equal to 0, and you are trying to overfit this value. Okay, now there is a problem again. You can make this infinity. Now you have to somehow penalize your function in order to not make this plus infinity, and in order to make a sensible function. So what you should do is you should somehow add something or somehow subtract something and do something to the function so that it does not overfit or it does not underfit. Okay, so that thing is called as a regularization. I hope that you are able to see the problem. The problem over here was, so when you were giving this value like a really high value to this, so the whole point was that this all this w transpose xi, the values were either plus infinity or minus infinity. So when this was plus infinity, so what will happen is, so it will correctly classify all the points, but the problem there is it will overfit the model. And generally what happens when you have overfit model, so it will give the high training accuracy, but when you test the model, it will not give good accuracy, because you basically try to memorize the thing, you try to overwork the thing. And that's why we use the technique of regularization. So what is this regularization? It's a technique by help of which we add some terms to the loss function. So we had this loss and we'll add a subtract something from the term so that it penalizes this. So if it wants to make an infinity, so you have to penalize it somehow. Okay, that these things are called a regularization. So here we will use what is called as L2 regularization. Okay, they're called as ridge and lasso regularization, and I won't tell you the names. I just want you guys to find the name. So what we'll do is now we'll just do one thing. So W star, if we have to find this, we'll say this is arc min of W. Find such a W such that for all the points, this log of 1 plus exponent of minus I think yi w transpose xi. They should be minimized. So now I'll add this. I'll say w transpose w. Okay, I'll add this term and I add a lambda. Okay, so this now becomes my hyperparameter. Okay, hyperparameter. So what this term does is, like, focus over here. So what this term basically is, this is second norm to, like, basically square. So you have a vector w, you just perform the dot product of this and square the thing by itself. That's what this w transpose w gives you. Okay, that's why it's called L2 regular, because this is L2 norm. So we have studied about these L2 norm equilibrium distance when we were, I think in KNN we discussed all these distances, Minkowski distance and this a lot of distance we said, and there we said in the algebra also we had discussion about these norms, L1 norm, L2 norm, and some things like that. So here if you see, these are parameters. So now what will be the effect of this term? Okay, so here what I am saying is this W transpose W plus lambda, I am adding this term. This is called as a regularization term. So this term over here is called as L2 regularization term, L2 regularization term. So here this is our loss. So this over here is our loss. Okay, now I have to minimize this. So now you cannot give the infinity value. Why you cannot give the infinity? So let's suppose you have to minimize this function. So you know that this point, this part of the function, this loss will be minimized if you give infinities to this. So if you give infinity, but since you give infinity, this will become minimized, but this will get maximized. So they are somehow balancing each other. So if you give this infinity value, this will really become small, but here this will become really large. So now both of these are having some sort of fight within each other. So if you increase this much, so I'll accordingly decrease the thing. If you decrease the thing, I'll accordingly increase. So if you increase the value of W transpose, I'll accordingly increase it here. Maybe you are getting decreased, but here the value is getting increased. So do you see the effect? So this is some sort of effect, cancelling out the effect. So if you give the W very high value, you give infinity's value. Now you are making a short thing that this term will get minimized. But you know that we have just added this regularization term. So what will happen there is, so from that this term will get again infinity. So you are not minimizing the thing. As a whole you have to minimize this now. How many of you are able to see this? So if you give W is infinity, maybe you will minimize this, but you'll again get a maximum value for this. Are you able to see it?
Yes, sir.
Okay, so what I'm saying is, if you take this W such a way, now what will happen in these W's? So you will take the values of W such that that both of these are balanced. This will also become the overall the function will get minimum value if you see this part and if you see this part. So you will give W's such a value so that both of these will give some minimum values. So all together you will have to see the overall effect. So overall effect will be that both of them when you take them in the overall thing, so you will give this minimum value. But if you just wanted to make this infinity, then you saw the effect out there. You clearly see that this term over here, this regularization L2 regularization term, this will become way high. This lambda here is a happy parameter. So in KNN, our happy parameter was K. So in naive base, our happy parameter was alpha, that's smoothing factor. So if you show that Lopel smoothing factor, if you sort of remember that. So here we have this lambda. So lambda here is a term. Let's suppose if lambda is 0, say we have this lambda. So lambda is equal to 0. So if lambda is 0, okay, that means this whole term will vanish away. Okay, whole term will vanish away. Now you will again overfit. Okay, will again overfit it. If now you keep it as 1 directly, okay, then again you have chances to underfit. So it is better that you have this lambda value somewhere between like 0, 0.3 or something like that. It depends, and you have to, and we'll see different methods how to tune these parameters. I hope that this is clear. So if you make this lambda very large, if you make not even 1, I'd say 100,000 or something, so this term will have more impact now. So you will have to have such lambda such that it does not impact, like it does not basically refrain this loss from getting minimized. So this point, so if you make this very large, again there will be a problem. If you make this very small, you are vanishing the whole thing. Okay, now you have to control this lambda. Okay, if this lambda is really 0, it will overfit. Okay, if this lambda is very large, if this lambda is having high value, so it will underfit. It will underfit the model. Okay, so by overfit I mean it is high variance model. This is high variance, and we call this model as high bias. High bias models. I told you that in machine learning the whole problem is to find the best fit model to balance in these overfitting underfitting. That's why we add these regularization terms, L2 regularization. We have something called as L1 also. Okay, so what is this basically? If I just have to write this W transpose W, W transpose W, this basically is nothing. So if you have this is summation of I will say W take Wj square, okay, and j is equal to some 1 to d, let's suppose, if it has d components, if it is W or 1 to n maybe. Okay, 1 to n. So our vector is like this. This is W1, W2 till Wn. So here we have again W1, W2 till Wn. So this is W1 square plus W2 square and so on till Wn square. This is how we can write it like this. So that's what I wrote, W transpose W lambda. This basically can be written as lambda times summation of I is equal to 1 to n or j is equal to 1 to whatever Wj square. So you can add it like this. Okay, here you can also expand this similarly. So I hope that this is clear now. So what does the regulation do? It prevents the model from getting either overfit or underfit. So what is the meaning of overfitting? So overfitting means the model tries very hard to learn every distribution. So underfit means it does not try at all. So that's why you should have you should fit these this lambda such that your model is a best fit model. Okay. There is again another regular called as L1 regularization. L1 regularization. Okay, instead of having this L2 norm 2, now what you can have is you can just have mod of this Wi summation of I is equal to 1 to n. You can just take mod. Initially you are taking square of this. Okay, if you know, so that's why we wrote it I or maybe W square L2. This is L2 norm, and this we call as L1 norm. Okay, this is L2 norm and this is L1 norm. L2 norm, you square the thing. You basically try to compute I is equal to 1 to n Wi whole square. Okay, and in L1 norm you'll just compute the absolute value. You'll compute the absolute value and keep on adding. This is called as L1 norm. You can just add this L1 norm over here. So is it clear? So how many of
Yes, sir.
you understood this? Why do we add regularization? Because the thing in regularization, we try to control the models overfitting and underfitting. I told you there is a again always a tussle between overfit and underfit. So how do we check? And we saw that you can also use cross validation, k-fold cross validation to check. Now here you can add the regularization terms also in order to see if the model is overfitting or underfitting. Okay, so you can also use this L1 regularization or L2 regularization, and sometimes we call it an elastic net regularization, elastic net regularization. Pardon my spelling. So where you use both of these, you use combination of this L1 and L2. Okay, you are now saying I'll use lambda 1 of this L2 norm, W transpose W, you'd use this, and plus lambda 2 of this L1 norm. Okay, this is L1 norm of this, and plus this is my loss. Okay, whatever loss function I have, now I'll use this lambda 1 and lambda 2. So we call this elastic net regularization. I have written it for here. So this is elastic net regularization, where you now you have two hub parameters. You have lambda 1 and lambda 2, two hub parameters. Okay, so there are a lot of methods where you use this. So I hope that you understood this L1 regularization L2, and in practice you will see that what is the benefit of this. So I do not want to get in that detail because it requires a knowledge optimization. Why do we use L1 regularization? Because in L1 regularization, if you use that, the unimportant, basically less important, they become 0. So I'll just write that line maybe. First, I'll have a discussion on that, this W vector, importance of this W. Maybe we'll just have interpretability of this vector W, of vector W. Okay. First, we'll interpret this W, what this W says. Okay. So now you know that this basically, if you see this W vector, so W vector is perpendicular to our plane. So this is our W vector. This is if you find a pi hyperplane, so this W is perpendicular to that. Now this W vector will be like this. So we'll have W1, W2, and so on till Wn. These are our components. So if you see, so these will get multiplied to this. So we have W1 x1 plus W2 x2. This x1 is the feature 1, x2 is feature 2, x3 is feature 3. Accordingly, we have the features. Okay, plus W3 x3. These are features like that. Okay. Now you see that these W's basically they get multiplied to the features. Now this says the importance. These W's tell us the feature importance. Okay. So if our let's suppose if our W is very high, say we have this, we have 1 to the power 1 plus, and you can see it like this. I will show it like, what is that? This over here. So this is our W vector. Okay. Now let's suppose we have feature 1. We have some feature, and if that feature increases, so if we have this W has some value, high value. Okay. Okay. Now we have this xi feature 1. Let's suppose feature. Since this feature increases, so what will happen is, so now you know that this value will increase. Basically, what I'm trying to convey is that these W's will be having high values if the feature is more important. In nutshell, I wanted to tell you this. So if we increase the, if we have this x, if somehow it gets increased accordingly because it's getting multiplied with that W, so overall you will maximize the equation. So okay, if you see this argmax of W, if you see the initial equation that we had, yi W transpose xi. So what I'm saying is this basically is again a dot product. So now if you have xi, as xi increases, okay, that means this whole sum will get increased. Similar for wi. So what I'm saying is if the component of W is more, that means that component is of more importance. Okay, that feature is of more importance. So we have this W1 x1 plus W2 x2. Now you know that these features are fixed. More the value of this W, it says that the vector is more important because you somehow want to maximize the sum. Okay, is it clear for everybody? So this W
Yes,
vector
sir.
is interpretable. How? So you'll get these coefficient values for something. You'll get coefficient values. So you are saying that if this W1 is high, that means the X1 feature is more important. If this W2 is high, the X2 feature is more important because this is coefficient of X2 features 2. Accordingly, if let's suppose W100 is having high value, that means X100 100th feature of that data point is more important based on the W, because this is how because we want to maximize the equation. Okay, we want to maximize the equation. More the higher the value of W, we are saying that feature is more important. So why do we use this L1 regularization? Is because when you apply this L1, it makes this Wi 0 for unimportant features. Okay, that is the reason. So we use L1 regularization sometimes as it makes Wi corresponding to feature I 0. Okay, if it's unimportant, if feature is very less important. That's why we use these L1 and L2 regularizations. Okay, you saw that this W again interpretability. If you have to take again guess the interpretability, you'll just see the values of W's. Okay, you will see what are the values of W's correspond to the features. If the value of W is more, you can say that maybe feature is more important than others. Okay, is this clear? I
Yes,
hope that
sir.
this is clear now. Okay,
Yes, sir.
I think before going to the probability interpretation, we should have some probability background. So in the next class, we'll be giving the probability background. But before that, I just wanted to tell you about the loss functions. Okay. So we have and the interpretation. Now we saw that the first interpretation we saw geometric, and we saw geometrically how to formulate this function and how to get to this equation, how to get to this equation basically. Okay, maybe in your project assignments you will be using this, and you will have to play with the regulation L1, L2, L1 and L2, and maybe combination of this elastic net you will use. And this is the equation that you have to remember. And now we can also use loss function. Okay, we can also use loss function. Okay, you can also use loss function to reach at the conclusion. So what's the meaning of loss function? Anyone? Do you know what's the meaning of loss function? I think we have discussed in detail. So what is the loss function? So loss function basically is a metric by which you evaluate how much better is your model. So you want your loss function to minimize, you want to minimize your loss function. Okay, if you remember that binary loss, we said that what will happen is if you have a correct classification, you'll add something, and when you have correct classification, you will not add anything, you will add 0. So for correct classification, you will add 0. For misclassification, you will add 1. Okay, so that was our binary loss, or we call it 0-1 loss also. 0-1 loss or binary loss. Okay, so what was that? That was if you have 0. So for that it means you are not computing anything, you are not basically computing the loss. But when you are making a misclassification, that time you are adding something to the loss function. So you will add for all the points I goes from 1 to n, you will see the cost of that. So what is the cost? So if it's a correct classification, you will add 0. If it's a misclassification, you will add -1, and you want to minimize this. And this over here is called as loss function. This over here was called as loss function. Okay, so you basically wanted to minimize your cost, minimize your loss, or we can say loss. It's sometimes also called as cost. So here this is a loss, so we want to minimize this. So this we have 0-1 loss. If you see 0-1 loss, how does it look? It looks like something like this. So if it gives value 0, so this is value 0 for the points which are correctly classified. Okay, and then it gives loss 1 for the functions which are misclassified. Okay, this is the function that we have, and you have to minimize this function, and you want to basically get the minimum value of this function. Okay, but the problem with this 0-1 loss is if you know how to minimize a function. If you have a function like this, so you have a function, let's suppose you want to find argmin, and you want to find values such that a function, let's suppose we have this is our loss function, f of x is our loss function, you want to minimize this function, and let's suppose this 0-1 loss is a function, and you want to minimize. How do you minimize? You use the differentiation. But what will happen here? So if you see this function is some sort of function which is discontinuous, it is not continuous function, so this won't be differentiable. That's why we have been discussing about differentiability, limits, continuity. If a function is continuous, then only will it be differentiable. So this function is not good, because if you have to find its optimal value, it is not continuous, it won't be differentiable. So we'll try to find a function which is differentiable and then compute the loss. Okay, so that loss function is called as logistic loss. So what you will do is now you'll just use this loss function. So what you will do, yeah. So if I just search on the web logistic law, I'll show you that. Just wait a second. So if you see it over here, so we had this loss. So here is the 0, 1 loss function. So here that's why it's written as 0, 1. So 0, 1 loss function is not, but we want to approximate it. Now we'll use logistic loss. So here it is a logistic loss. This loss is logistic loss. Okay. Now if I want to show you the expression of this, so this is the expression. So I can write the expression. So here is the expression. So this is called as logistic regression law, and this function is called as logistic loss function, this function over here. So don't you see that this is the same function that we derived from the geometric interpretation? Okay. So how many of you understood this? So this is the little loss function that is given to you. Now you have to minimize this loss function. This is the logistic loss. So this is the loss function formulation. Okay. Again, I'll write it over here, maybe with the red, if it is visible. So what we had this function. So we'll take for all data points from 1 to n. So we'll take log of 1 plus e to the power minus yi w transpose xi. Okay, so this function over here is called as logistic loss function. As we saw that we had binary loss function, 0, 1 loss, and we have also hinge loss. Okay, we have a different type of loss function. So this is called a logistic loss function. So in loss function, if you just change it to hinge loss, so this will give you logistic regression. This will give you logistic regression. So if you change this function, let's suppose to hinge loss. Okay, if you change it to hinge loss, so what will happen is, if you change it to hinge loss, you will get SVM, support vector machines. That is the beauty of these loss functions. Okay, so if you just recall the first lecture, we said that we define a loss function from the optimization perspective. So we just want to minimize this loss function. So we want to get the minimum loss. So for this logistic regression, this is the loss function. You can directly go and use the loss function. But in order to understand it fully, you have to have the geometric intuition. How do we get to that loss function? But otherwise, you can directly go to the loss function, because I said that there is a whole pipeline of this thing. You have the data, and then you define the loss function. Okay, you penalize your model somehow. So this is how we penalize our model. Okay, you can directly understand this from the loss function perspective. Okay, but I just wanted to give geometric intuition so that you understand how do we arrive at this loss function, and why do we need such a loss function. Okay, similarly, if we now use, instead of this loss, this is called a logistic loss. If we use hinge loss, we'll get to support vector machines. Okay, something like that. And there are different loss functions which will take you to different algorithms. Okay, by changing the loss function, you will change the algorithms. Okay, this is the interpretation of loss function. Okay, if you have a loss function and you use that, it is basically making algorithm. I hope that at least geometric interpretation was clear to you. How do we arrive at this? And now you can directly use this loss function as it is. Now in the next class, we'll see the probabilistic interpretation. So basically in that, I'll try to go from naive Bayes to logistic regression. So I'll basically show you, if we have naive Bayes and then we make one more assumption. So we'll go to logistic regression. Basically, assumption there we'll make is, we'll say this this belongs to, this is a Bernoulli random variable. But for that, you'll have to understand what Bernoulli random variable is, what is the Gaussian distribution, and then we'll go from naive Bayes to logistic regression, and then we'll prove it probabilistically. Basically, we'll again land up at this loss function. Okay, so we'll again land up at the loss function that we have over here. Then we'll add some regularization. Regularization term is not there in loss function. Okay, this is our loss term, and then we have a regularization term that is there to prevent the overfitting and underfitting. Okay, because you have high chances, if you have that, if you do not set that lambda, you'll go w is equal to infinity and you will overfit the model. That's why you control that lambda, you control the hyperparameters. And then we'll also see how to basically find the best hyperparameters. There is something called as grid search. We'll use that grid search to find that best hyperparameters. I hope that you are clear with logistic regression so far, except for this probability interpretation. Maybe from the next class onwards, we'll first again cover the probability, random variables, what are some type of different distributions, so that we can understand this logistic regression from the probabilistic interpretation. Okay, so I'll stop the recording over here. If you have any